Okay, let's have a class, and before we talk about vinegar, we'll do a very quick review what we talked about on Tuesday about the sugar, the carbohydrates, the number one. So carbohydrate, we talk about the first section, which is monosaccharides. Saccharides. Monosaccharides, and we were talking about using glucose as an example. So we mentioned about the glucose. The structure of the glucose, we mentioned it is CHO, C and H, OH, C, H, OH, H, then go here. We had a center which is a 6 carbon, and center is 4 carbon, so CH2OH. And we say this structure is called Fischer projection. And the same as we talk about the lipids, and the chiral carbon right here is on the center. So we have carbon number 2, number 3, number 4, number 5. These we call it chiral carbon. So what we talk about that. And why the Fischer projection we could do? Because it looks like a slash and also the wedge form, and we talking about going this angle is 45 degrees using the eye to see it. But this is like a 2D configuration. We're not going to see the spatial view. So lots of the time we will be writing glucose looks like a ring structure. And this ring structure looks like this. OH, H, H, OH. Then go OH, H. And then we go here is H, OH, and this is H and CH2OH. And we talk about that. This is configuration, we call it a Haworth projection. And the Haworth projection, we could see the spatial view, because we could see the structure there. And we also mentioned about there is a transition step. At the beginning, there is a 7C carbon, 7C ring. It is rejected by the nature because it's thermodynamic unstable. So finally, we actually become is a 5 carbon ring. And we said from the Fischer projection to the Haworth projection, and what happened here is the chiral carbon, which is increased from 4 to 5. So the chiral carbon is increased from by 1. Haworth projection, remaining a question is right here. You see right here, there is a hydroxy bonds could be up and down. And using Haworth projection, sometimes it is a little bit hard to see. So the chemical area, they come out with another very interesting structure, which is we actually call its chair configuration. Okay. The chair configuration is I said it's really challenging to draw sometimes. Especially I'm not very good at drawing, so I just draw like that. And we mentioned about here, the H always is in a axial position, and then the OH all the time, which is actually a little bit angle, but we call it is equatorial position. Now, based on the equatorial position of the hydroxy bonds, we could separate them into alpha and beta anomer, we call it. And we also said our nature likes beta more, so there's approximately 64%, which is beta anomer, and the alpha anomer is about 36%. And then we know how they got this results is a crystal sugar dissolved in the warm or the acid, slight acid solution, and then they find it is a mixture of all the isomers, so they give them a terminology which is called multi-rotation, which means this is a mixed isomer. Mixed isomers, okay? Then we also give you some of the conclusion. We say, regarding the isomers, there are 4 different types of the isomers. Number 1, we call it constitutional isomers, which means that is aldose versus ketones. That means it's aldehyde versus ketone structure. And we also talk about the enantiomer. This is the one I forgot to mention about. This is really depends is on the for actually it is rely on is on carbon number 4. It is rely on that. We talk about is L and D. Okay, so that's carbon number 4 decided by D or L, and our nature prefers the D. That is about 99%, and the L configuration, it is only about 1%. Majority of that time it happens in the polymers. Oh, sorry, it's in the polysaccharides. Then we talk about the others, including the anomer. And the anomer, we talk about alpha and beta configuration. So that's carbon. We also call it anomeric carbon, and we mentioned about here. And the last one we also talk about is epimer. So epimer, which means their structure, most of them are the same. The only one thing difference. Let's say glucose versus mannose, the only difference is at the carbon number 2, left and right. And we also mentioned about the glucose and a very important sugar, which is called galactose. The only difference is in the carbon number 4. So these are the things we mentioned the last time. So just give you a brief review. We talk about these monosaccharides. There is one thing I want to check to see what there's one thing I want to check to see that I missed here. Okay, we also talk about once this happens, relate to the multi-rotation. This is we also call it's a glucopyranose. So glucopyranose ring will be generated. Okay, rings will be generated. So these are the things we mentioned. Now, last thing we forgot to talk about here is how many isomers will be generated for the monosaccharides. The number of the isomers, which is calculated by the number of the chiral carbon. So that is equals to times the power of n, and that m equals the number of chiral carbon. So for example, if you have a glucose, which have 1, 2, 3, 4, 4 different type of the chiral carbon. So what are the isomers for glucose? To be honest, if you theoretically, that is about 16. And that tells us every single hexo, which means there are 6 carbon monosaccharides, theoretically they will have 16 isomers. And if it's pentose, then that will have 2 times the power of 3, that will have 8 isomers. And you could do a calculation, but the formula is 2 times the m equals the number of the chiral C. Okay, so this is what we talked about already. We'll just give you an overview. Oligosaccharides will be followed to talk about the monosaccharides that we will talk on Tuesday, next week Tuesday. Because it's a food microbiology class, so more or less we should know about the processing, especially related to the sugar. So therefore today we want to talk about is a vinegar, how the vinegar will be generated. Okay, so that's why the topic is a vinegar manufacturing. So give you a very simple opening remarks. Vinegar, where that comes from, is said very easy. This is a secondary fermentation of wine. Some older research, they say the wheat products also could be generated vinegar. But most of the time it's a second fermentation of wine. So said very simple. If you have a bottle of wine at home, okay, let's just say like that. This is the wine, let's say. Red wine, white wine. And then you didn't eat it, you didn't drink it, you loosen the cap, which means the oxygen could come in. And then the major components of the wine, of course, is the alcohol, is the ethanol. Then they will be reacted. After about several weeks, several months, even half a year, then you open this bottle. You see the wine is no longer wine, it is very acid. And it tastes like, you can even smell it, and it tastes like acid solution, completely acid solution. That is a vinegar, actually. However, it may not be edible, which means it's not drinkable. Because we didn't do any of the treatments to make sure the yeast is gone and the waste product is gone. But I tell you, the easiest way to have a vinegar is just to open a bottle of the old wine and let it be sitting in the room temperature, exposed to the oxygen for 3 months or half a year, then you open it, it looks like a vinegar. So that tells you, this means the secondary fermentation of the wine, which means you have an ethanol generate and you continue to do the fermentation will generate acid, okay? So the second question will be, what is the components of a vinegar? The vinegar, the commercial products most of the time is 4 to 8% of acetic acids. Now, if we buy a bottle from Kruger or somewhere, lots of the time they will label 5% acid. That means it is approximately 5% acetic acids. So let's talk about this acetic acids a little bit. So what is acetic acids? We already know. This is CH3 COOH. It could be written by C2H4O2. But this doesn't tell you anything. It is only tells you the components is carbon, hydrogen, and oxygen. Looks like we're back to our first class. So what is this is really for? This one, we call it acidic acids. But we have another name. We call it ethanoic acid. So what is ester means? This ester means it is two. So what is the acidic acid originally from? Originally it should be looks like this. Just simplest like that. Originally that is what it looks like. Two carbon. Then from the chemistry standpoint, they do some of the reaction. They took this down. They replaced this with this guy, carboxy group. So it becomes CH3, double bonds O, and OH. Now how do we know this? This is the carboxy bonds. We have OIC, anoic. This means carboxy acid. Okay, so that's what the acidic acids originally comes from. So that's the second question we want to say. Now, third question: what are the overview material to make a vinegar? The overview material to make a vinegar, we need to have a substrate. So substrate. Well, substrate, you always remember we need wine or we, but basically is wine. And what else we need? Oxygen. That's very important. That's the key. We need oxygen. Okay, what else we need? We need the bacteria. Okay. What are the bacteria we need? There are basically two bacteria. One bacteria is very easy to understanding because it will generate acidic acids, so it is called Acetobacter. It's very easy to understand. The second one, because originally the reaction coming from the starch, then becomes maltose, and it becomes glucose. There the bacteria could do it is gluconobacter. So that's the second bacteria could do using during the vinegar manufacturing products. Now what is the product? Of course we know it's vinegar. So this is another one we talking about from the reaction standpoint. What are the things we need? Now, what is the overview biochemistry reaction for vinegar? So we're going to draw from the top. Okay, so originally from the beginning we have starch. So what is a starch? We'll talk about it. It's a polysaccharide. So there's a C6H10O5. Because it's a polysaccharide, so we just write it in. And starch cannot be used because it's too huge. The molecular weight is too huge. So we need some kind of enzyme. The enzyme is called amylase. This is everybody knows. Then it becomes what? Become a maltose. Maltose is two glucose they combine together. And later on will be more hydrolyzed, become glucose. That is C6H12O6 becomes a glucose. Okay, now the glucose comes out. The glucose need a yeast. So we just say wine yeast. The wine yeast, Saccharomyces cerevisiae, which is a wine yeast. then it will be going through fermentation. So the fermentation products will generate alcohol. Okay, so alcohol will be generated. So what is that? This is C6H12O6. This will be C2H5C. This is C2H5OH. Now, of course, there's a water that comes out. So that's ethanol comes out, the alcohol comes out. Then we'll be going through a relatively longer process. So we had alcohol, C2H5OH. And we generated through the yeast from the glucose. And this process we already talked about in the fermentation process. This is called hetero fermentation, because it's generate final products is not acid. It is other than acids, it is alcohol. And we also talked about before, it's the homo fermentation. If you remember the homo fermentation, which means it is a pyruvate will become lactic acids. And this is of course accompanied with NADH oxidized become NAD plus. And this whole process is only A2 ATP generated and coupled with glycolysis. Okay, that's something we just do a brief review. So we had alcohol. Then what we're going to do, working with oxygen. Okay, then you go this process. They need an enzyme which is called acetaldehyde dehydrogenase. This is a very simple words. What it means a dehydrogenase, you take out of the hydrogen. That's why we call it a dehydrogenase. It's an enzyme. So what's the product's going to generate? CH3OH. Then what is this guy called? Sorry, CHO. CH3CHO. Very simple. We call it dehydrogenase. Product name acetaldehyde. So this is acetaldehyde. Comes out. Now acetaldehyde is not enough. It stays there. And this process is part of the fermentation process. It also coupled with NAD. NAD reduced to NADH2. They coupled with a reaction. Okay. Now acetaldehyde has to do something. So acetaldehyde will work with water, but they're not going to work separately. They need an enzyme which is hydrase. Because you're going to add a hydroxy bond there, so it becomes CH3CHOH2. What is this? Acetaldehyde hydrate. Okay, this is the process almost down. So we go here. We don't need so many hydroxy bonds there, hydroxy groups there, because finally we only need one. So what happened here? We still need to take out of the proton. So this is called, the enzyme is acetaldehyde dehydrogenase. And then finally will become CH3COOH, then become acetic acids. And this process also needs is NAD reduced to NADH2. Okay, so that is the whole process, what it comes from. There is a chemistry reaction behind it. So we talk about here is from the chemistry standpoint, what the vinegar manufacturing will be coming. Then we're gonna go into see, Gary, do you mind move it? Then we're gonna move on to the steps, which is how the manufacturing really, just make it flat, that way. Yeah, a little bit flat, because otherwise the border will be the yes, that's good. Yeah. So we're going to talk about the real methods. So the manufacturing methods, there is three methods from the small producer to medium and to the large industry, what they do. The first methods, we call it orange methods, or orange process. We know New Orleans, but all the time they call it orange. It didn't really happen just in Louisiana State or the southern part nearby there. That's back in like 98, like 80s and early 1900s. This is basically for the small producers they do. So they had a big tub like that. Like a general tub, you just put it horizontally. Okay, now on the bottom here, we need to put a tray, and tray will be collect waste. All kinds of the waste we have collected. And then in here, we're gonna put is basically we put a tab. Okay, a valve, a tab. So the tab, you could have collecting the vinegar products. Liquids. Okay, now this whole tub, the volume is approximately 600 to 700 liter. But we're not going to fill all of them with wine. We basically will be do somehow around 70%. Okay, we say 60 to 70%. So how many we do? Around 300 liter, or some people will say 200 to 300 liter. The wine we're going to put in there. Okay, we put these wine there. Now where the wine going to come in, most of the time they do a hole on the top, which is they call it a sub, or we call it a funnel. We call it a sub. The wine going to be coming right here. We're going to drip it. Now what do we need? We need to add bacteria. So we just let the bacteria float it on the surface. Okay, that's a bacteria. So we need a bacteria, and we say the bacteria is Acetobacter, or Gluconobacter, we already mentioned. Now what else we need? We need oxygen. We need to make sure the oxygen is always coming. So the oxygen is going through the filtered mesh hose, we call it. So what happens is usually at the end of these, we dig a hole there, and then right in the middle, they also dig several holes. They have these holes there, but what they have is they use mesh. Now why? Because in the old time, in the small producer, these mesh has to be prevent the dusts. We don't want the dusts there. We don't want the rats there. Think about it horrible, because the maintenance going to take a longer time. It's going to be one process about a week. It could take a month or a couple months. We don't want to see the rats is jumping there later on, and also the pets. We don't want them. You don't want to see the cats sitting there, so they have to prevent that. Now this whole process, because it's very simple, following the chemical reaction doesn't do anything to epithelize the process. So that took a longer time. With Oren's methods, the fermentation took basically is a week at least. So that means 7 days. And how many they will be generated? This is the process. Usually they will generate 60 to 70 liter vinegar. About a week. And every week we have to refresh, add a new wine there. Refresh 10 to 15 liter the new wine. We have to add it. So make sure this whole process is always have a fresh wine there. Okay? So that's very slow. The reaction is relatively slow. But they do using for the small producers to generate these products, the vinegar. So later on, for the medium producer, they generate a second method, which is we call it trickling method. So what's a trickling method looks like? They're using a relatively large tub. The tub is relatively large. And then the same thing, at the bottom, they need to add a pan there. Okay, that is for a tray for collecting waste. That's the same thing as before. Okay, then we have, it could be go here. There is a valve, there is a tap. This is tap to collect vinegar. And then what do they do? They have a control panel here. The control panel accompanied with a hole. They will let the oxygen gonna go there. And they're trying to control, which is the temperature. They try to let the temperature at the bottom is 35 degrees Celsius. And at the top is around 28 to 30 degrees Celsius. Why? Because the air, warmed air, is always trying to go up. Okay, so this is about in your home, in the summertime, you're always feeling your second floor is a little bit hotter than the first floor, the basement is relatively cold. So let the air go up. And then at the top, you're going to have these type of the sprayer comes out. Now, of course, somehow you do like that. You let the sub is there, you let the wine come in, and this is like a shower. So we say it's a wine shower. Let it be dripping, let it drip. And this makes oxygen goes up. Now what else we are missing? We said very important is a bacteria we need to be there. Acidobacter or gluconobacter. Now what we do? If you just put a bacteria there, it's a very large volume, it's going to go everywhere. So what they do, they put a lot of thing, which is called beechwood shavings. So what's the function for the beechwood shavings? Beechwood shavings have the very large, we call it extended large surface area. The large surface area will let the bacteria grow. The bacteria will inoculate, they're going to attach to it. not only they attach to it, they're going to attach it firmly, and finally, they will become a very important structure called a biofilm. That is a matrix of bacteria. They connected with each other, going through coring sensing process, will be attached firmly. Biofilm originally in the food industry, it is a harmful bacteria because it's resistant to the sanitizer. If you on the bench, the food processing plant, the bench has a meat residue and you didn't do a sanitation standard operation procedure very well, then the biofilm got attached to it. And then the second day you go ahead to sanitize it, makes it very hard to remove. However, here we added beetroot shavings to make sure the bacteria could attach to it, and the bacteria is largely existing and fully exposed to the oxygen surrounded there and with the wine. So this is actually which is speed up the fermentation process. So speeding up the fermentation process around 72 hours. And finally, this temperature is about 32 degrees Celsius. So 72 hours, you could get a vinegar. So that's you're already halfway done compared to this orange methods. But what's the disadvantage for this? You're gonna have lots of these beetroot shaving. Okay, you have these lots of beetroot shavings. Then this is used a lot, and you could refresh it. Well, I don't know how often it's going to be refreshed. I mean, the extension specialist, some university will tell you about it. They have to refresh. But then more and more you come, it becomes a waste. So where are they going to go? So there is a story before the beetroot shavings was using. In the old time, they think this method is too slow, so they're going to add something there. They are thinking about just using corn. Because corn, you have these niche there. Is that right? You have lots of niche there. Lots of shavings going to come out. So you can just dump a couple of corn there and let the bacteria attach to here. They have a biofilm film. But the concern is that this is going to be very heavy and large, more and more waste are going to generate. So later on, they think about using the beetroot shavings. Okay, so that's the second method. The idea here is speed up the fermentation process with extended area for bacteria reacted with the oxygen. Now, start from the 1950s. The company has been, lots of the company generate those mass production facility. We call it is a bio generator, which is submerged bio generator. So that's called a submerged bio generator method. So how they do it? Very similar, not a big difference. So you have these, okay. This time they have the hole right here. So this is going to be the tab to collect it. And they have a control panel right here. This will be a temperature control panel. And they also have a control panel right here. So that will be the oxygen control panel. Okay, it's more standardized. And on the top, you're going to have something coming. You're going to be the raining of the wine comes in. Okay, now they're not going to using any of these shavings because we mentioned it's a waste. What they do, they're going to add a blade fans. So like at a fence, and let it be spin rapidly, so let's oxygen reacted more often. Well, of course, there is a control panel could be controls the speed somewhere right here, okay, for the speed control. Of course, you have to inoculate the bacteria. So this is where let the oxygen is more often contact with the wine and also with the bacteria. So this will be shortened fermentation process to only 24 hours. Another thing is that because you have a temperature control, you can increase the temperature. So the temperature basically will be increased from 30 to 35 to 42 degrees Celsius. So let's the fermentation temperature a little bit higher and also speed up the process. This is the production rate. Usually a week will generate 2,000 to 3,000 liters. About a week. So that's a lot of the mass production will be generated. Okay? Now, of course, more and more new technology will come in. Methods will be improved a lot, but this is in all the textbook. Very traditional, talk about the development from orange methods to trickle methods and the submerged biogenerator to generate the vinegar. From about 60 to 70 liter vinegar a week, this guy around 200-ish, 200, 250 liter. And finally, you could generate thousands about a week. Okay, so its production is improved. Okay, so vinegar, we finished talking about that. I have slides for that. I will be uploaded onto the eCampus. You can read. Next one, we want to talk about some of the fermented products, but we'll be focused on the plant produce fermented products. I will talk about 3, but most likely talk about 2, folks. Sauerkraut. Okay, sauerkraut. So first of all, what is sauerkraut? Long time ago, not really long, 5 years ago, when I first teach this class and also have a general microbiology lab, we made it as a sauerkraut. So we made a shredded lettuce, immersed into the salt solution. And I have a very good student, Derek Warren. He became an assistant professor in the University of Arkansas. And I asked him, I said, what it tastes like. He said, it is a salty lettuce, salty shredded lettuce. Well, I think it is described very well, tells you 2 information make sauerkraut, which you need a salt solution and you need a shredded lettuce. So let's talk about that. First of all, sauerkraut comes out is more than 2,000 years ago. It's not new, it's very old products. Originally that coming is Dutch, we call it sea trading. We have called Vinegar, which means they are doing the business from the Western Europe to North America. Today we know that if you are flying from Pittsburgh to London, I did it last year, it only took you 7 hours for direct airlines. Then you go London, you could go everywhere, take the train, but in the older time, it took about at least 1 to 3 months from Western Europe to the United States. If they just shipping through the Atlantic Ocean. So what's the problem for those business person in the boat? The problem is that they lack vitamin C. Vitamin C is very important because if you do not have enough vitamin C, you will have anemia. So what we have to do, they are trying to do a safe way. And they're also trying to solve the food security problem, which means the products should have a longer shelf life. They want it to be, hopefully it can sustain a couple months, so they have this sauerkraut comes out. Okay. Now, why they will have an idea about the sauerkraut? Because they find about that the sauerkraut, the vitamin C, is about 38 to 55 milligram per gram. This is around 0.28 to 0.48% if you do a titration. So that means it should be good for the daily supplements if they can make sure that vitamin C is enough about that. So this comes out where the sauerkraut in the history. So how we do it? We could do this in the lab. It is very simple, not difficult. You have those shredded lettuce. Okay, this is the shredded lettuce. You put it there. Obviously, you're gonna put the water, but the water is not really a simple water. It's a salt water, salt solution. Now, what's the concentration of the salt? It is somehow 2.25 to 2.5%. This salt solution is very important. Why it is important? There is a several function for this salt solution. Number one, we will inhibit gram-negative bacteria growth. Lots of the bacteria will be killed by the salt because it's unbalanced of osmotic balance. Lots of the gram-negative bacteria will be killed, and some of